Consider a meter stick, common in physics classrooms. Every part of the meter stick is pulled downward by gravity, as shown by these sample vectors. All the vectors added together make up the weight of the stick. The average downward pull of gravity acts at a certain point, called the center of gravity. For the stick, the center of gravity is at the 50 centimeter mark, where we place a dot. We can support the weight of the stick by a finger placed just below the center of gravity. Then the stick is in equilibrium, where your applied force F balances its weight mg. We can also talk about the center of mass of an object. That's the average location of all the object's mass. In everyday cases, center of mass and center of gravity are in the same location. So we can use center of gravity and center of mass interchangeably. Where's the center of gravity or center of mass of a donut? Aha, it's in the center of the hole. So center of gravity or center of mass on something may be in a location where no mass or weight exists. And we see that the center of gravity of a boomerang, likewise, is where no mass or weight exists. When the boomerang is tossed in the air, it appears to wobble all over the place. What place? That's right, the center of gravity. It's the center of gravity that follows a smooth path as the boomerang wobbles about it. Consider this L-shaped piece of plywood. Its center of gravity, like the boomerang's, is at this point, outside the mass. This is the average location of all the wood's weight. For some purposes, it's as if all the wood's weight is located there. Because of its center of gravity, balancing of the wood can be interesting. Let's drop in on an early City College of San Francisco conceptual physics class and see how balancing such a piece of wood leads to a fascinating topic: torque.
Let's suppose I want to balance this like this, except for the motion this way. We see it doesn't rotate this way, does it? Because the center of gravity is right here, and boom, there's a support underneath. But how about I tip it like this? You know it's going to topple over. Everybody knows that. Children know that. It's going to topple right over. Now, we have a way of looking at that. Let's look at it on the board. Here's my L-shaped object sitting on the table. Center of gravity of that object is right about here. That means old Mother Earth is pulling down on that object as if all its matter were right there. And so we can draw an arrow down here for the weight. But notice something. This force pulling down is not supporting. It rocks about this part here, doesn't it? This is like a seesaw rocking, or something that's rocking. It's going to rock about an imaginary fulcrum. You know what a fulcrum is? The middle of a seesaw, the fulcrum is the part about which rotation takes place, okay? Or if I take this book and I rotate it, the fulcrum would be what? Right in here. The point, the axis of rotation, okay? So here's my axis of rotation right in here. And so I get a pull, whoop, a flip, or a rock right over. Now it's going to rock right over like that because of something we haven't discussed yet. This force gives rise to a twist. Loosely speaking, you can say we have a twisting force here. But non-loosely speaking, that twisting force is called a, anyone know? Begins with T, ends with orc. Torque, okay? It turns out you will have a torque on this object. And let me define torque. Torque is the product of how hard something pulled, force, by the leverage arm distance, the lever distance. So what we have here is a torque, a force through some leverage distance. Now what's the distance? That's crucial. The lever arm distance is not the distance between the point about which rotation takes place and the center of gravity. That is not the leverage distance. The leverage distance is this distance in here, that distance. And the lever distance is always the shortest distance between the axis of rotation and not the point of application, but the line of action of the force. This force goes all the way down. That line of action, right here, and that the shortest distance right in there. It's always a right angle. You take that force, multiplied by that distance, you will have a number which is called torque. And if you have an unbalanced torque on any system, that system is going to change how it rotates. We say it will rotationally accelerate. So if it's at rest to begin with, and it's a torque, whoop, it's going to flip. Over it goes.
Back to our screencast. A nice way to distinguish between force and torque involves this activity, which you should try for yourself. If you hold a meter stick at one end with a stick extended horizontally and with a weight suspended from its midpoint, you feel a rotational tendency of the stick. You have to hold it tight and give it some opposite twist, that is, some opposite torque, to keep it from rotating. If the weight is moved to the end, holding becomes more difficult. But wait, there has been no change in the magnitude of force involved, just a different location for the force. What you feel isn't a difference in forces, what you feel is a difference in torques. As mentioned in the classroom lesson, we define torque as torque equals force multiplied by lever arm distance. In the first position, the distance between your hand and the hanging weight was less than when it was moved to the end of the stick. What has changed is the lever arm. When the lever arm is doubled, the torque, which you readily feel, is doubled. People who use tools are familiar with the torque produced with a common wrench. Here we see your hand exerting a force on the end of the wrench. What you want to do is rotate the bolt, colored purple here, that's in the jaws of the wrench. For maximum torque for a given force, you exert the force at 90 degrees, a right angle to the wrench handle. We see the lever arm is just about the length of the handle. If you instead exert the same amount of force at a non-right angle to the handle, the torque you'll provide is different. Here's my question. In which of these two cases are you more likely to turn the stubborn bolt? Did you say the first case? If so, you're correct. And did you reason that the lever arm is greater in the first case? Yum to that. We see in the first case the lever arm is the full length of the wrench handle. The lever arm is the perpendicular distance between the pivot point and the line of action of the force. Note the shorter lever arm distance. Perchance the bolt is really stubborn and you can't get it to rotate, extend the lever arm with a pipe. Now you can exert even more torque. Yum! I want to leave you with a question. If you use a pipe to extend the lever arm of the wrench, so your grip is 3 times as far from the bolt, and you pull twice as hard as before, at right angles to the pipe, by how much will the torque you produce increase? That's the grip is 3 times as far, and the pull is twice as hard? Think about that. Until next time, good energy. Let's look at the physics of a playground seesaw. We show the fulcrum with the triangular-shaped support. It's the point about which rotation takes place. A little girl sits at one end of the seesaw, and her boyfriend sits at the other end. Both the girl and the boy have equal weights. We label the forces involved, mg for each kid, and the normal n, the combined weight of the kids acting up at the fulcrum. The forces balance, and we see that the sum of the forces equals 0, the equilibrium rule in action. The kids are able to rock the seesaw up and down by leaning forward and backward in a way slightly shifting their weights. Kids do this all the time. But suppose one of the kids moves closer to the fulcrum. The system is no longer balanced. The girl soon rotates onto the ground, not shown here. For balance, a heavier kid needs to sit where the first boy sat. Then his weight multiplied by his closer distance to the fulcrum will equal her weight multiplied by her distance to the fulcrum. This brings us to a second requirement for mechanical equilibrium, that the sum of the torques on a system also equals 0, where Greek letter tau stands for torque. Equal and opposite torques can produce mechanical equilibrium. Let's drop in on one of my early City College of San Francisco conceptual physics classes and see this physics, not with a seesaw, but with a classroom meter stick.
Look at seesaws. Right now, I have my pivot point, the center of gravity. So what do we find? No rotation. It's not exactly centered in there. You get the idea, though. Put a weight over here. What happened? Wow. Put another weight over here. Now I'm talking about something you're all familiar with. Isn't that right? If these weights are the same, up and down, and this distance are the same, then we say the amount of torque that's tending to rotate it this way is just counteracted by what? An amount of torque rotating this way. And if those torques are the same, then I'll have no net torque, I'll have no rotation, if it's not rotating to begin with. And there we are. Isn't that neat? Now you know what's going to happen if I move this one in. I still have the same force acting over here, but I don't have the same torque. That's because my distance is less. And now it goes like that, okay? But I could have something like this. I could have playing with another partner. Suppose I could get something like this. You see, you don't have to have equal people, equal mass people playing on the same seesaw. Can you see that? Now, when it comes to balance, when it does, true or false, this weight multiplied by this distance will be exactly equal to this weight multiplied by this distance. Check the neighbor. Anyone say false? Okay?
Let's go back to our seesaw. As we've seen, kids can balance on a seesaw even if they have different weights. Whether they realize it or not, they position themselves so that the sum of the torques cancel to 0. Their torques will be equal and opposite. That is, the torque produced by the girl on the seesaw tends to rotate it counterclockwise, while the torque produced by the boy tends to rotate it clockwise. The two rotational tendencies cancel out. The torques are balanced. Here's something interesting. Even if the girl hangs below her end of the seesaw, balance remains. Why? Because although she's farther away from the fulcrum, her lever arm hasn't changed. The lever arm is the perpendicular distance from the fulcrum to the line of action of the force she exerts on the seesaw. We show the line of action with this purple dashed line. This imaginary line coincides with her weight vector and extends from far above the girl to the center of the earth. The distance between the left end of the seesaw and the fulcrum is the lever arm, always at 90 degrees to the line of action. Recall our treatment of a wrench in our previous screencast, where we defined the lever arm as the perpendicular distance between the line of action of a force and the pivot point. Getting back to our seesaw, we assume that the girl sits 3 meters from the fulcrum, the lever arm distance. Here she dangles 4 meters below the end of the seesaw. What's her physical distance from the fulcrum? That's right, 5 meters. Never mind the 5 meter distance. Her lever arm, as said, is 3 meters. just as it was before she decided to play around. Yum, physics? I hope you think so. Let's conclude with an intriguing situation. Suppose our boy has no friends to play seesaw with. If he can reposition the fulcrum, would he be able to play by himself by leaning to and fro as with a partner? Wouldn't the seesaw itself be his partner? We show the seesaw's center of gravity with a purple dot at its center. I want to leave you with a question. Suppose the boy succeeds by sitting on the far end after shifting the fulcrum beneath the seesaw's 1/4 mark, as shown. For rotational equilibrium, how will the boy's weight compare with the weight of the seesaw? Think about that. Until next time, good energy. Phil Physiker's pet dog Bo is sitting on one end of a long uniform plank that extends beyond the edge of the top of a building, indicated by the gray region. Bo has weight, W sub Bo, and the length of the plank is L. If the plank and Bo overhang too much, Bo is in trouble. Let's draw a fulcrum here at the edge of the building. That's the point about which the plank will rotate if it gets extended too far and tips over. Our question is, what maximum distance can the plank extend from the edge of the building? That is, from the fulcrum. Here's where the concept of torque and center of gravity come in. The weight of the plank acts as if it's concentrated at the plank's center of gravity. When the plank is at its maximum safe overhang distance, the torque due to the weight of Bo just balances out the torque due to the weight of the plank. Here the Greek letter tau stands for torque. We see that Bo is at a distance x to the left of the fulcrum. The center of gravity of the plank is at its midpoint, distance L/2 from the left edge of the plank, which means that it's at a distance L/2 minus x from the fulcrum. Equating torques, the weight of Bo times distance x will equal the weight of the plank at its center of gravity times the distance L/2 minus x. Doing a bit of math, we see that Bo can safely overhang the building's edge a distance equal to the plank's weight divided by the sum of the two weights times L/2. Beyond this distance, toppling occurs. To make better sense of this, let's suppose the weights of Bo and the plank were the same. Then we'd see that the equal weights of the board and Bo ought to be equal distances from the fulcrum, like twins on a seesaw. Equal distances would put the fulcrum midway between Bo and the plank's center of gravity. That's a distance 1/4 the length of the plank, distance L/4. Let's consider another plank and torque problem. Again, a heavy plank rests on the top of a building. Nellie Newton stands at the edge of the plank of length L that extends from the top of the building as shown. We assume that the maximum distance of overhang for tipping cannot occur beyond 1/8 the length of the plank. Nellie's weight is W sub n, and the weight of the plank, centered at its center of gravity, is W sub PL. Question: how does Nellie's weight compare with the weight of the plank? Again, the edge of the building acts as the fulcrum about which tipping can occur. When the plank is at its maximum safe overhang distance, the torque due to Nellie's weight just balances the torque due to the plank's weight. So how far is the plank's center of gravity from the edge of the building? It's L/2 from Nellie, so the distance is Some arithmetic here. L over 2 minus L over 8 out to be 3L over 8. So our dimensions are shown. And setting the torque due to Nellie's weight equal to the opposite torque due to the weight of the plank, we see that Nellie's weight is 3 times the weight of the plank. Notice that I underestimated the length of the vector for Nellie's weight in my sketch. Looking backward, it should be 3 times the length of the vector for the plank's weight. Yum stuff? I want to leave you with a question. If you balance a horizontal meter stick on a finger, you'll place your finger at the 50 centimeter mark. But suppose you balance 2 meter sticks, one attached by tape to the end of the other and hanging vertically as shown. For the 2 meter stick combination, at what centimeter mark of the horizontal meter stick should you place your finger? Think about that. Until next time, good energy. As with all sports, there's a lot of yum physics in the maneuvers associated with skateboarding. I've marveled as to how my grandson Alex, a skillful skateboarder, is able to perform such feats as jumping with his skateboard to elevated surfaces. He crouches and then springs upward along with his skateboard in a jump called an ollie. Let's look at this in slow motion. While heading for the elevated surface, he exerts a downward force on the tail of the board, producing a torque about the rear wheels. This rotates the skateboard upward, raising its center of mass as it becomes airborne. But controlling the lift goes further. When airborne, Alex slides his forward foot toward the nose of the board, which produces a second torque, this time about the center of mass of the board. The resulting motion levels the board for a yum landing. So there are 2 torques a skilled skateboarder employs. The one of slamming the tail of the board into the ground that pivots the board about the rear wheels. And when airborne, a second and smaller torque that pivots the board in the opposite rotational direction about its center of mass. When both torques are executed, 2 separate rotations about 2 axes control the board. Yum rotational physics. I want to leave you with a question. How does the upward curved surface of the tail of the skateboard enhance lifting? Until next time, good rotational physics. For centuries, people have wondered about the role of the moon on ocean tides. Here's the moon, in empty space. Not quite so empty, for in its vicinity, let's suppose there's a giant blob of water. For the moment, we'll assume both are at rest. If no external forces act on the giant blob, it's pulled inward by both surface tension and its own gravity to take the shape of a sphere, the shape having the least surface area. But there are external forces on the water. The moon exerts gravitational forces on the blob and forces that are not uniform. Since the force of gravity between 2 bodies varies as the inverse square of their separation distance, the moon pulls harder on the parts of water closer to the moon than on parts farther away. If the body of water is closer to the moon, the elongation is more pronounced. Not only are the forces greater, more importantly, the difference in forces between the closest and farthest parts is greater. Opposite sides of the blob seem to be stretched apart. Let's move the water back a bit and put planet Earth in the middle of it. And let the planet spin, say 1 rotation each day. Looking down on the North Pole and watching Earth rotate, an observer at the seashore notices that the water is deep here, a high tide. Oh, notice the water is becoming less deep. And here we're at low tide, the best time to dig clams at the beach. Then the water begins deepening again, and before you know it, we have another high tide. The cycle continues. This computer animation makes this clearer. Nearer the moon, we see a greater stretch. Put a solid body inside the blob, move it out a bit, and here we see a North Pole view of Earth rotating daily beneath the ocean bulges. So with each rotation of Earth, we get 2 high tides and 2 low tides. So we see how Earth is elongated by the difference in lunar poles on it. The elongation is on opposite sides of Earth, so it doesn't make sense to think that the elongation is only on the side of Earth that faces the moon. A corresponding elongation occurs on the moon as well, even though it's solid. Consider the elongated moon, as I'm drawing, very much exaggerated to help me explain an age-old question. Why does only one side of the moon face us? The moon, like all bodies that rotate, rotates about its center of mass, shown by this purple dot. Here's a situation where the center of mass and center of gravity don't coincide. Because one side of the moon is closer to the Earth than the other, the close side is more gravitationally tugged toward Earth than the farther away side. This results in Moon's center of gravity being somewhat closer to Earth than its center of mass. I draw this with the red dot. And a purple dot for Earth's center of mass. This red vector from the Moon's center of gravity is the gravitational force that Earth exerts on the Moon. The Moon's long axis, through both its centers of mass and gravity, is shown by this white dashed line. The result is a torque about the Moon's center of mass, which tends to rotate the long axis of the Moon into alignment with Earth's gravitational field. We see the same behavior with a compass needle that aligns with a magnetic field. Once aligned, the torque no longer exists. The alignment of Moon's long axis continues as the Moon circles Earth. We say the Moon is tidal locked to Earth. How about that? Now, getting back to ocean tides. It so happens that the Sun also plays a role in ocean tides. Because of its vast distance from Earth, the difference in its poles on near and far sides of Earth are much less than Moon's difference in poles. Although less than half as effective as the Moon in raising tides, Sun's influence is there because it's so massive. Most noticed when the Sun, Moon, and Earth are aligned. Here we see the Moon in its new moon position. Tidal influences of Sun and Moon coincide when this alignment occurs, producing extra high tides and 6 hours later, extra low tides. At times when the alignment is perfect, so the Moon casts a shadow on Earth, we have a solar eclipse. But that's another story. These greater than average tides are called spring tides, although they have nothing to do with the spring season. Spring tides occur at or near the time of a new or a full moon. When the Moon is not in line with the Sun, when it's positioned 90 degrees to the line between Sun and Earth, tides due to the Moon and Sun partly cancel each other. That occurs when an observer on Earth sees a half moon in the sky. How do you think tides are affected at this time of month? Did you say smaller high and low tides then? If so, you're correct. These tides are called neap tides. Our treatment of tides is simplified. Average high tides are only a meter or so above the average surface of the ocean. So the bulges we depict are greatly exaggerated. And why the tidal bulges don't line exactly with the Moon or Sun, why they don't occur at the same time each day, and why variations in tides occur in different parts of the world, these all make up another story, a fascinating one. I leave you with a conservation of water type question. Suppose you go to the beach to dig clams at the time of an extra low tide. Is it reasonable to assume that in about 6 hours, the high tide that follows will be extra high? Think about that. Until next time, good energy. Things that rotate, whether a habitat in space or an athlete doing a somersault, remain in rotation until something interrupts their motion. A rotating object has an inertia of rotation. This is akin to moving things having an inertia of motion, which we've called momentum. The momentum we've discussed so far has been linear momentum. Now we discuss angular momentum. We see Phil Physiker whirling a tin can in an overhead circle. The can has momentum, its mass multiplied by its speed. Looking further, we see the can also has angular momentum. In the simplest sense, we define angular momentum as the linear momentum multiplied by a radial distance. That's angular momentum equals the product of mass times speed times radial distance. If we multiply the mass of the can by its speed and multiply this by its radial distance, that's its distance to the center of its circular path, we'll have the can's angular momentum. And just as a net force is needed to change linear momentum, a net torque is needed to change the angular momentum of an object. Phil Physiker says it well.
An object or system of objects will maintain its angular momentum unless acted upon by an external net torque.
A satellite orbiting a planet normally has no external torques acting on it and has a constant angular momentum. Multiply the mass of a satellite by its speed and the distance to the planet's center, and you'll know how much angular momentum it has. That angular momentum will persist until some external torque acts on it. If no torque, then it will continue in its motion indefinitely. Likewise with the planets that orbit the Sun and those orbiting other stars beyond the Sun. Angular momentum is a fact of everyday life for astronomers. Angular momentum and a related concept, rotational inertia, is nicely demonstrated in physics classes when the instructor stands on a rotating turntable. Let's see this by dropping in on one of my conceptual physics classes.
I've got down here a rotating platform. You see this platform, gang? It's a very low friction rotating platform. What I'm going to do is I'm going to stand on that platform. I'm going to hold these weights out. When I hold these weights out like this, I'm going to spin like this. When I hold them out far, do I have a lot of rotational inertia or a little? How about when I pull them in? A little? So if I get here rotating like this, and I hold them out, what happens when I pull them in? Ooh. Easier to rotate, gang. Harder to rotate. Easier to rotate. Harder. Woo! Woo! Okay. You see such thing? All right? All right. You go to the, ooh, a little kiss of this here. You go to the ice volleys, you see the skaters turning around like that, they're spinning, 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 and when they're spinning, they pull in like this, yeah? Go fast, 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 and then they come on. Da-da-da-da! People think they're going like that for applause. You know what they're doing? They're trying to save them from breaking their necks. You increase your rotation. Isn't that neat? Okay? So we can really see. You can try this after class. You got to try it to really appreciate it. See that? Yeah. Now, there's another concept here, gang. It's called angular momentum. Remember before we talked about linear momentum? Okay? There's a counterpart here.
Back to our screencast. So just as linear momentum is conserved in the absence of a net impulse or net force, we see that angular momentum is conserved if no net torque acts. We call this the conservation of angular momentum. Phil Physiker states the conservation of angular momentum.
If no external net torque acts on a rotating system, the angular momentum of that system remains constant.
Angular momentum conservation is nicely employed by figure skaters and gymnasts, especially when spinning and executing other maneuvers. I want to leave you with a question. Suppose you're at an amusement park and you sit in the middle of a large rotating turntable that is set spinning and then allowed to spin freely. When you crawl toward the edge of the turntable, does its rotational rate increase, decrease, or remain unchanged? What physics principle supports your answer? Until next time, good rotation.